Good afternoon, Mr. Bond. Yesterday you came in complaining of severe upper abdominal pain accompanied by nausea and vomiting. After blood tests showed your serum amylase levels to be 4 times normal, a CT scan found slight swelling in your pancreas, confirming a diagnosis of acute pancreatitis. I have here that you estimate your average alcohol consumption at roughly 5 vodka martinis per day. Is that correct? It is very likely that your high consumption of alcohol is at least partially to blame for your pancreatitis. Although the liver is the main organ involved in alcohol metabolism, the pancreas is also capable of breaking down ethanol and can suffer from the effects of excessive intake in the form of acute alcoholic pancreatitis. Before we get into the specifics of pancreatitis, let's look briefly at the basic structure and function of the pancreas as a whole. Pancreatic cells fall into 3 main categories: exocrine, endocrine, and stellate. Exocrine cells secrete products into ducts. They include ductal cells, which secrete bicarbonate to neutralize stomach acid, and acinar cells, which secrete inactive forms of digestive enzymes called zymogens. Stellate cells either store vitamin A or mediate inflammation depending on whether they are active or quiescent. Endocrine cells secrete hormones into the bloodstream. In the pancreas, endocrine cells are clustered into groups called islets of Langerhans. Within these islets, alpha cells produce the hormone glucagon, beta cells produce insulin, and delta cells produce somatostatin. Although all 3 cell types can be affected by pancreatitis, acinar and stellate cells are most important in understanding it. Now back to alcohol. How does it cause the pancreas to become inflamed? There are 2 main types of alcohol metabolism, oxidative and non-oxidative, both of which occur in the pancreas and produce damaging byproducts. In the oxidative pathway, alcohol dehydrogenase, abbreviated ADH, converts ethanol to acetaldehyde and reduces NAD to NADH. NADH is a high-energy electron carrier which can be used to synthesize ATP via the electron transport chain. But acetaldehyde is extremely toxic to cells and can easily damage the pancreas or the liver. Therefore, acetaldehyde is quickly brought into the mitochondria where it can be converted to acetate by the enzyme aldehyde dehydrogenase. Acetate is released into the bloodstream where it can be used to produce carbon dioxide, water, and fatty acids. When excessive alcohol is consumed, alcohol dehydrogenase is not able to keep up with alcohol metabolism on its own, and cytochrome P450-2E1, abbreviated CYP2E1, is recruited to help. Unfortunately, CYP2E1 not only forms toxic acetaldehyde, but instead of producing NADH, it makes reactive oxygen species. These run amok, altering DNA, RNA, proteins, and lipids via oxidation and severely damaging the liver and pancreas. Think of alcohol metabolism as dealing with a mouse-infested house. ADH is like hiring an exterminator to kill the mice slowly and methodically, and acetaldehyde is like the bodies of mice killed in the process. It takes a while for the exterminator to get there and remove traps, and maybe you'll step on a few of them and hurt your foot before all the mice are gone. It's expensive, it's not painless, and it might smell a bit bad until the exterminator comes back and removes all the traps. CYP2E1 involvement is like having a house so full of mice that the exterminator, who now seems to be of dubious repute, decides to employ the animal shelter to help out as well. Sure, your mouse problem goes away quickly, but now you're left with a house full of cats scratching up your furniture and peeing on the carpets. You've replaced an alcoholic mouse problem with a quite formidable reactive oxygen cat problem. So what exactly do acetaldehyde and reactive oxygen species do to pancreatic tissue? Within the pancreas, high concentrations of alcohol dehydrogenase enzymes are stored within stellate cells. Under normal circumstances, these star-shaped cells mostly store vitamin A. However, exposure to reactive oxygen species, or the acetaldehyde produced by their very own ADH enzymes, causes stellate cells to become activated. activated stellate cells grow and divide rapidly. Instead of storing vitamin A, they start synthesizing extracellular matrix proteins, especially collagen. This accumulation of ECM proteins eventually leads to fibrosis, or a buildup of scar tissue so severe that it impairs the ability of the pancreas to perform its normal endocrine and exocrine functions. Compared to the liver, the pancreas has a lower concentration of ADH and CYP2E1 and a higher concentration of FAEE synthase. FAEE synthase catalyzes the second route for alcohol metabolism, combining ethanol and fatty acids to form fatty acyl ether esters, or FAEEs, in what's known as the non-oxidative pathway. Once produced, FAEEs activate IP3R calcium channels in the endoplasmic reticulum of acinar cells, which leads to a massive increase in cytosolic calcium concentrations. When ER calcium levels drop due to sustained IP3R opening, the protein STIM1 binds to crack channels, which bring in more calcium from outside the cell to slowly replenish ER stores. This process is partially countered by active transport of calcium out of the cell, but high levels of FAEEs are enough to keep acinar cytosolic calcium concentrations continually high. So why is it so bad that acinar cells have a little extra calcium? One problem is that acinar mitochondria normally take up calcium and use it as a signal to produce more ATP. When calcium levels are high for too long, mitochondria take up too much calcium and eventually lose membrane integrity. This triggers both controlled death, known as apoptosis, and uncontrolled death, known as necrosis. Another problem is that ERs experience severe stress due to uncontrolled calcium levels from sustained IP3R and crack channel opening, as well as inconsistent ATP availability as the mitochondria starts to fail. Acinar ERs are important for synthesizing digestive enzymes such as trypsin. Because these enzymes can break down pancreatic proteins if active, digestive enzymes are produced in their inactive form called zymogens. These are later cleaved to form active peptidases in the duodenum of the small intestine. For example, trypsinogen is activated to trypsin by enteropeptidase, which is found in the brush border of the duodenum. Brush border peptidases cleave zymogens in the lumen of the duodenum without them ever needing to enter small intestine cells. Trypsin and other activated digestive enzymes are then free to break down their respective macromolecules within the duodenum, which, along with the rest of the downstream digestive tract, contains a protective mucosal layer to prevent digestive enzymes from contacting epithelial cells. Think of the pancreas like a truck transporting a tiger from a zoo back into the wild forests of the duodenum. Ideally, we want the tiger asleep while in the truck and awake once we get to the jungle. If the tiger wakes up too early, we can expect a more damaged, and perhaps more digested, truck than we had hoped for. The exact mechanism by which trypsin is activated in acute pancreatitis is not fully understood, but one theory is that cathepsin B, a protease normally found in acinar lysosomes, is instead placed into zymogen granules when the ER becomes stressed. Once cathepsin B is distributed into granules, it activates the zymogen trypsinogen into the potent digestive enzyme trypsin. Unlike the duodenum, the pancreas does not have a mucosa to protect against digestive enzymes, so premature trypsinogen activation can cause severe damage as the pancreas is quite literally digested from within by its own enzymes. Okay, James, all that sounds scary, right? The good news is that your pancreatitis is acute and mild, and all you need today are some pain meds. However, the fact that you developed pancreatitis once means that you likely have a genetic predisposition for it, which is related to your ability to metabolize alcohol. If you keep drinking like this, the pancreatitis is likely to return. If it does, you are at extreme risk for developing chronic pancreatitis, which could require surgery to remove damaged pieces of your pancreas and often leads to a lifetime of pain. They might also require you to take supplemental insulin and/or digestive enzymes to make up for the loss of pancreatic function caused by fibrosis. Aside from quitting drinking, there is currently no medication approved to prevent your acute pancreatitis from becoming chronic. However, a study from 2022 found reduced chronic pancreatitis after treating rodents with pirfenidone during episodes of acute pancreatitis. Pirfenidone has been shown to reduce inflammation and fibrosis in acute pancreatitis, which is unsurprising as it is already approved to treat pulmonary fibrosis in humans. Decreasing accumulation of scar tissue during acute pancreatitis is crucial in preventing the more permanent and more devastating chronic condition. Pirfenidone mainly reduces fibrosis by blocking activation and production of TGF-beta1, a growth factor which signals the cell to deposit more ECM proteins such as collagen. Pirfenidone also scavenges radicals to reduce ROS formation, reduces collagen mRNA transcription, and inhibits production of heat shock protein, thereby decreasing transformation of procollagen into collagen. Additionally, continuing to drink like this predisposes you to pancreatic cancer, which has a 10-year survival rate of less than 5%. Even if you do not develop chronic pancreatitis or pancreatic cancer, this level of alcohol consumption could cause similar issues in your liver, including inflammation called hepatitis or scarring called cirrhosis. Now that you understand the gravity of the situation, let's work together to find resources that can help you reduce your alcohol consumption and prevent any future complications.